Hello and welcome to Note Quiz number 12, which is all about exponential and logarithmic equations and applications. Before we get into those, what we want to do first is talk about some of the properties of logarithms. And if you remember, logarithms are the inverse functions of the exponential functions, so therefore it's kind of safe to think about logarithms as exponents. In other words, they follow the rules of exponents. So we'll kind of put that over here in quotes. Logarithms are exponents. So as we go through these different properties of logs, we're going to be asking ourselves about exponents as well. So the first rule that we're talking about is called the product rule. And it says when you multiply two things with the same base, you add together the exponents. And therefore, the log of a product is the sum of the two logs. Then we have a quotient rule. Remember in exponents, when you divide two expressions of the same base, you subtract the exponents. Well, here, when you divide inside of a logarithm, you subtract those logarithms. So division turns into subtraction. And then the next rule, the power rule, says that the power on the expression inside the logarithm comes down out front. And that is your power to a power where we multiply exponents. And then finally, these last two rules here are called the inverse rules because remember that the logarithm and the exponential function with the same base are inverses. So these cancel out when they're composed in either direction. Again, those cancellation properties that we see later will play a big role later. I can write the word cancellation a little better than that, I believe. So again, these are called the cancellation properties. And we'll use them in the middle part of this note quiz. So for this first problem in our logs, what we want to do is we want to take apart logarithms using those three properties that we start off with. So in the first problem, you'll notice that we're taking the log base 5 of 25 times x. So again, that multiplication is going to turn into addition. So this is the same thing as log base 5 of 25 plus log base 5 of x. And we can simplify this down a little bit further because log base 5 of 25 is just 2 because 5 squared is 25. So this is 2 plus log base 5 of x. All right, so that's our first problem there. Get a little bit of a better plus sign. There we go. For the next one, you will notice that we have division inside of our logarithm. And from above, we see that division turns into subtraction. So this is the natural log of the number e minus the natural log of the number 11. And the natural log of e is just equal to 1 because e to the first power gives you e. So this is the same thing as 1 minus the natural log of 11, which is our final answer for our simplified expression. For our next two problems, you will notice that we have exponents this time. So for the first one, we have log base 10. We're not writing it, but there's a base 10 there because that's a common log. And we've got a 5. That 5, again, we said from property 3, can come down as a coefficient on the logarithm. So this is going to be 5 times log base 10 of 3t plus 9. And those parentheses here on this logarithm are very important because that whole inside part belongs together. So 5 times log base 10 of 3t plus 9. For this next one, you'll notice that we have division happening. We have some multiplication and some exponents. First thing I recommend doing is taking apart the division. This is going to be log base 6 of my numerator, which is m to the 7th, minus log base 6 of my denominator, which is n to the 6th times p. And we now have multiplication to take apart in the second logarithm. So that's log base 6 of m to the 7th minus log base 6 of n to the 6th, and now minus log base 6 of p. That minus that's in front of that logarithm belongs to both terms. So when you break apart that over addition, that minus gets distributed to both. One last step here is noticing we have exponents. Again, those exponents come down as coefficients on the logs. So we're going to bring those in front of those and get 7 log base 6 of m minus 6 log base 6 of n minus log base 6 of p. And we have our logarithm completely broken down. And the idea here that even though this may not look simple at first, the idea is that we took exponents and division and multiplication and turned it into just adding and subtracting logs with coefficients, which makes it a lot simpler to work with. And if you ever take calculus someday, you'll notice it's a very important strategy for doing things in that course. So let's move on to the second page, and the second page has us looking at a very complicated problem. We want to simplify the logarithm with a whole bunch of multiplication, division, and a radical. So the first thing you want to do in this problem is break it apart using the division rule. So this is going to be equal to log base 10, again, the base doesn't play a role in this part of the breakdown process, of 100 times y times 8x plus 5 to the 7th minus log of the cube root of 8 plus 5x. And you could put parentheses around that, or you don't have to. Next thing to do is break apart this logarithm further. So we've got those 3 multiplications. We've got log of 100 plus the log of y plus the log of 8x plus 5 to the 7th. And then back here, I'm going to rewrite that cube root using a fraction exponent. That is 8 plus 5x to the 1/3 power. Next thing for us to do is to bring down our powers. This is a log of 100 plus the log of y plus 7 log of 8x plus 5 minus 1/3 log of 8 plus 5x. And we're almost done, except that first term is actually just the number 2 because the log of 100 is 2 because 10 squared is 100. So that's just a 2. So our final answer is 2 plus the log of y plus 7 log of 8x plus 5 minus 1/3 log of 8 plus 5x. And again, that log is completely simplified down. We can't go any further with this simplification. All right, now let's move on to the next problems, and that's going to have us going in reverse. In other words, we're going to take expanded logarithms and rewrite them as single logarithms. And in doing so, when we get into more complicated problems, you'll notice that we do the last steps of breaking down first when we're going backwards. And we'll talk more about that in a minute or so. So for this first problem, we're looking at the log base 6. This subtraction of 2 logs is going to turn into division. This is log base 6 of the fraction 108 over 3. And again, this is where subtraction of logs is just the same thing as the log of a quotient or a division. And we can actually reduce down 108 divided by 3. That's actually 36. So this is actually log base 6 of the number 36. And that's just equal to 2 because 6 squared is 36. So this actually simplifies all the way down to a 2. For the next problem, you'll notice that we have coefficients on our logarithms. So we're going to first bring those up as exponents. So this 5 comes up as a power, the 6 comes up as a power, and so does the 7 come up as a power. So this is log base 6 of r to the 5th, minus log base 6 of s to the 6th minus log base 6 of t to the 7th power. And now we're going to rewrite this as one single logarithm. Remember again, subtraction turns into division, and it's one single log. So this is going to be log base 6 with a fraction with r to the 5th upstairs and s to the 6th, t to the 7th downstairs. So again, log base 6 of the fraction, r to the 5th over s to the 6th, t to the 7th. Remember again, you're going to have one single logarithm as your answer. And again, a way to check this is keeping in mind that negative exponents are reciprocals. So those two minus terms, which are negative terms, they go down in your denominator when you find and build your fraction. All right, so move on now to the next problem, which is number 8. This one looks a little bit like a doozy at first. So let's kind of go through and do this in steps. There are a bunch of different ways to handle this problem because we have a fraction of 1/4 in front. So some people could go in if they want to, and they could multiply the 1/4 in. And let's do that because that's what I did in class. So when I multiply through by the 1/4, I'm going to have first 1/4 times 12. Well, 1/4 of 12 is just 3. All right, so now we're going to move on to exponential equations. And exponential equations are where we have the unknown and the exponent. And there's two different kinds we're going to see. We're going to see problems that have common bases and problems that don't. So in the idea that we have common bases, if you know that the bases are the same, then the exponents must be the same. So the idea here is to get both bases equal so you can compare and set equal the exponents. Same thing is true for logarithms. If the log of two things are equal with the same base, then the insides, which are called the arguments, are equal as well. So let's move on to this first problem. It has a lot of space, but there's not a lot of work. Again, the idea is to look for a common base. And if you think about it, 2 raised to the 5th power makes 32. Because 2 times 2 is 4, times 2 again makes 8, times 2 again makes 16, times a 5th time makes 32. So 32 is the same thing as 2 to the 5th. And now that you have the same exact bases, you can just equate the exponents and you get x equals 5. So x equals 5 is the solution for the first equation. A very short problem. For the next problem, however, you'll notice that the bases don't look the same right now. One base is 3 on the left. The other one is 1/9 on the right. So the idea here is to rewrite the 1/9 as a power of 3. And if you think about it, if you take a 3 and you flip it over and then you square it, that does make 1/9. So that exponent is -2. So this is 3 to the 3a plus 1 equals 3 to the -2, all raised to the a minus 3 power. And now we can simplify this down. That's 3 to the 3a plus 1 equals 3. Remember, when you raise a power to a power, you multiply them. So that's a -2 times a plus a 6. And now that the bases are exactly the same, we can equate the exponents. That tells us that 3a plus 1 equals -2a plus 6. And then I can quickly solve this equation algebraically by adding 2a to both sides and subtracting 1 from both sides. And I end up with 5a is equal to 5, dividing by 5, of course, to get the a. And I get a equals 1. So that's the solution for that exponential equation. All right, next up, you will notice that we have an 8 and a 32 for bases. For these equations here, we're going to be looking at finding a common base. And you might think it might be 8, but 32 is not a power of 8. You might be thinking of 4, but 4 and 32 are not powers of 4. They actually are powers of 4 if you get into radicals, but we're not going there. But you could do it that way. Instead, the idea is to rewrite these both as powers of 2, because 2 cubed is 8, and 2 to the 5th is 32. So for the first one, this is actually 2 to the 3rd power raised to the 2x minus 3 power. And the other side, the right side, the 32, is 2 to the 5th raised to the x plus 2 power. And then remember, just like before, when you raise a power to a power, you multiply. And also keep in mind that you got to distribute when you're multiplying. So this is actually 2 to the 6 times x minus 9 equals 2 to the 5x plus 10 power. And now that the bases are exactly the same, we can equate the exponents. So that takes us to 6x minus 9 equals 5x plus 10. We can now solve by subtracting 5x from both sides. We can add 9 to both sides. And that takes us to x is equal to, looks like 19. All right, so x equals 19 is the solution for that equation. And again, that is another example of having a common base. Now for this problem here next, you'll notice that I've got 2 to the r power is equal to 17. Well, no matter how hard you try, you're not going to be able to express 17 as a power of 2. So what we have to do instead is think of another way to undo, hint, hint, exponents. And you are right. If you're thinking logarithms, that is the way to go. Now, technically speaking, you can use any logarithm you want, but I'm going to use the natural log in all of these problems because the natural log is on a calculator, and more importantly, it is a little less writing. So I'm going to take the natural log of both sides. The natural log of 2 to the r is equal to the natural log of 17. This may look like I'm multiplying, but I am not. I am using a function process, similar to square rooting both sides or squaring both sides, and so on. Next thing to do is notice that I can use property number 3 from before. That exponent can come down as a coefficient. So this is r times the natural log of 2 is equal to the natural log of 17. And now to get the r all by itself, I just have to undo the multiplication by dividing both sides by the natural log of 2. So r is equal to the fraction natural log of 17 divided by the natural log of 2. Remember again, the natural log is a function, so please don't cancel the ln's. They do not cancel each other out. This is like function notation, like square roots or cube roots or squares. So the idea is that this is just going to be the exact answer of natural log 17 over natural log of 2. You can get a decimal approximation by going to your calculator. That will work out to be 4.0875. And you'll notice the answer is just above 4 because 2 to the 4th is 16 and 17 is just a little bit above 16. All right, so that right there is how we solve exponential equations when the bases cannot be related. For the next problem, we're going to copy it down because when I made these notes, it did not get moved on to the second page. So next up, let's take a look at problem 13. So problem 13 was, and that's the key word here, before I got lost in the copying process, it was 5 to the 7x plus 3 is equal to 3 to the 4x. And we want to solve this equation. Once again, you will notice there is no common base here because I cannot find a common base between a 5 and a 3. So instead, I'm going to use the inverse function, the natural log. So I'm going to take the natural log of both sides. The natural log of 5 to the 7x plus 3 is equal to the natural log of 3 to the 4x. Just like before, these exponents come down as a package deal as a coefficient. So I'm going to bring those both down. And now I've got 7x plus 3 times the natural log of 5 is equal to 4x times the natural log of 3. And now I need to solve for x. To do that, I'm going to first multiply out so I can organize everything. When I distribute on the left, I get 7x natural log of 5 plus 3 natural log of 5 equals 4x natural log 3. And then I can subtract the 4x natural log of 3 from both sides and subtract the 3 ln 5 from both sides. So when I do that, I'm going to have the 7x natural log of 5 staying put minus 4x natural log of 3, which came over to this side, equals negative 3 natural log of 5. And now I can factor out the common x that both these terms share. So factoring out the common x will leave me with 7 natural log of 5 minus 4 natural log of 3 is still equal to negative 3 ln of 5. And we almost have the x by itself. The last step is going to be to divide. And I'm going to divide the whole thing. So I'm going to divide by 7 natural log of 5 minus 4 ln of 3 on both sides. Now that right there is my exact answer, and I can write it in the square very carefully. So again, that's negative 3 ln 5 over 7 ln 5 minus 4 ln 3. If you put this into a calculator, you will get x is approximately 0.7026. And when you do put in a calculator, be very careful to make sure that you put parentheses around that entire denominator. It would be, now do this in a different color, it would be negative 3 ln 5 divided by parentheses 7 ln 5 minus 4 ln 3. And again, you'd put that into your scientific calculator and have it give you a decimal answer. On a side note, and I'm not going to spend any time on it here in this video, but you could also rewrite the x, if you wanted to, as the natural log of 125 divided by the natural log of 81 divided by 78,125. And you can see that if you go in and use the properties of logarithms to rewrite that as a simpler expression, kind of going backwards and doing the reversal of the expansion process. So again, we're not going to do it in this video here, but it is kind of interesting to take note of the fact you can rewrite that answer in a simpler way. All right, so for the next problem, this one's a little different because you'll notice that it's got the exponential function showing up a few times. So when you first think about this problem here, you should hopefully be thinking that it might look familiar. In fact, it looks a little bit like a quadratic equation. I'm going to go through and rewrite this as e to the x squared minus 7 times e to the x minus 8 equals 0. And now you'll notice that this is a quadratic equation if I replace the e to the x with a different variable. So I'm going to let u be e to the x. So now my quadratic equation is u squared minus 7u minus 8 equals 0. And now when you solve this equation here, you should always try factoring first because we really don't want to layer all of these different things on you all at the same time. So usually when a substitution is done, these problems are factorable. You will notice I can factor this as u minus 8 and u plus 1 that equals 0. And then if I set each of those factors equal to 0, I got u minus 8 equals 0, or I've got u plus 1 equals 0. So u is 8, or u is equal to negative 1. But I didn't want u's, I wanted x. So now I make the replacement that u is e to the x. So e to the x equals 8, or e to the x equals negative 1. And it should bother you when I write that second term, or that second expression, or equation I should say. It is impossible for an exponential function to ever give you a negative answer. So this right here is not possible, and we scratch it out. On the other hand, I can solve for x on the left side. That's going to just be me doing the inverse again. And again, the inverse of the exponential function is the log. And I might as well use log base e since it's an e problem. So I'm going to take the natural log of both sides. And when I do that, the natural log and the exponential function are inverses because they have the same base. So that's x is equal to the natural log of 8. So the exact solution here is x equals natural log of 8. As a decimal, x is approximately 2.0794. And by the way, if you were on autopilot and you did try taking the natural log of negative 1, you will get an error message because negative numbers are not in the domain of logarithms. They can only be positives. So one way or another, you're going to find out that nothing comes from that negative 1 in the solution process. All right, so let's move on now to the next page in the notes, and we're going to get into some applications. So for the next problem, we're going to look at a compound interest problem. And for a compound interest problem, there's two different kinds. There's the continuous, which this is, and that means that interest is being compounded at every possible fraction of a second. And then there's the other kind, which have monthly, quarterly, annually, semi-monthly, or daily, whole bunch of options. So in that case, you would use the formula A is equal to P times 1 plus R over N to the NT power, where the N is equal to the number of times per year compounded. But again, that does not apply in this problem because they're using the keyword here of continuous. So when you see the word continuous in the problem, it is this formula right here, which is often called the PERT formula. So A is equal to P times E to the RT. In this problem here, P is the principal, and that is the amount invested. R is the interest rate as a decimal. And T is equal to the time in years. All right, so for this problem here, what we want to do is set it up. And you will notice that we're going to start off with $11,000 being invested. And we want the money to double, which will become $22,000. They're telling us the interest rate is 7%. And they want to find out how much time it's going to take for this to happen. So when I set up my equation, I'm going to have my amount I want to reach, which is $22,000. My principal, again, is $11,000. E is just that natural number, E, and it's 0.07 times T. So that is the exponential equation that I want to solve. When I solve it, the first thing I want to do is isolate the exponential, which means I divide both sides by 11,000. And we'll get a very familiar number. We get the number 2 is equal to e to the 0.07t. And that makes sense because we are doubling our money. If you want to triple your money, you would see a 3 showing up there. If you're going to be quadrupling your money, it'd be a 4, and so on. So we really have e to the 0.07t equals 2. We're now going to take the natural log of both sides. And I'm going to kind of reverse the order around so it's a little easier to talk about. So the natural log of e to the 0.07t equals the natural log of 2. Remember again, this exponent will either come down, or in this case, because we're dealing with the number e, the natural log of e just cancels out, and they're inverses. So we get 0.07t equals the natural log of 2. Last step in solving this is divide both sides by the 0.07. And when I do that, I'm going to get t is approximately 10 years. So it'll take 10 years for my money to double in this account. All right, now let's move on to the next type of equation we're going to encounter, which are logarithmic equations. And you could either use the property where log base 2 of something equals log base 2 of something else, therefore the insides must be equal. But I really like to use inverse functions because inverse functions play such a big role in mathematics. So what I'm going to do instead is I'm going to cancel out the logarithms by using the exponential function. And you always want to use the same base that's given to you in the problem. So in this case, I'm going to be using big old 2's. Put a big 2 here and a big 2 there. And the exponential function and the log cancel out on both sides. And I'm down to just 9 minus z equals 3z plus 5. And again, that would have been the same thing if I just would have compared the insides of the log functions. All right, to solve this now, I'm going to subtract 3z from both sides, which again is using an inverse, by the way. Subtracting 9 from both sides. That's going to take me to a negative 4 times z is equal to a negative 4. Dividing by negative 4, I get z equals 1. And for this problem, you will notice that if I use a 1 in that function, on either side, I am not having the log of a negative, so I'm good. You will also notice this checks, by the way. 9 minus 1 is 8. Log base 2 of 8 is 3. 3 times 1 plus 5 is 8, and log base 2 of 8 is 3. So you get 3 equals 3 when you make the comparison. Now let's move down here. When you see a log all by itself again, that is a common logarithm. There is nothing wrong with putting a little tiny invisible 10 there on the logarithm as a reminder. So again, this is called a common logarithm. Again, a log without a number, it's 10. So this is really log base 10 of 3x minus 8 is equal to 0. If I want to cancel out that log function, I will use its inverse, which means I'm going to use a big 10 here and a big 10 there. Once again, the exponential function and the log are inverses. They cancel out, and I get 3x minus 8 equals 10 to the 0 power. And we all know that anything to the 0 power is going to be a 1. So that's 3x minus 8 equals 1. That's going to be 3x equals 9. And then dividing by 3, I get x equals 3. And that is the solution for that logarithmic equation. These equations are called logarithmic because the unknowns are inside of a logarithm. All right, so now let's move on to the next page. The next page has us dealing with an equation that has 2 logs and a miscellaneous number. So when I move on to the next problem, you will notice that I have to kind of do some organization first. And it's always a good idea to bring 2 logs over to one side and move the miscellaneous number to the other side. So I'm going to add the logarithm to both sides. And in particular, I'm going to add log base 3 of p plus 8 to both sides. I'm also going to add 2 to both sides so I can have everything sorted out. So now when I do this, I'm going to have my two logs on the left. I'm going to have the original log base 3, and I'm going to put parentheses around that p because it's important to make sure that p is kept away from the other things. And then that's plus the log base 3 of p plus 8 that I brought over. And that now equals 2, which I brought over from the left side over to the right side. All right, so next thing to do is, again, use those properties. I'm going to rewrite this as the log of a single quantity. Addition becomes multiplication. So this is going to be log base 3 of p times p plus 8 equals 2. And now that I have a single logarithm, I can now apply the inverse function, which is the exponential function. So I'm going to put big old 3's on both sides. And again, on the left, those are inverses. They're canceling out. So I have p times p plus 8 equals 3 squared. So now to solve this, what I want to do is I want to think of it as something that I've seen before. And this equation, when I distribute, is going to be p squared plus 8 times p is equal to 9 on the right side. This equation is quadratic, and I've got a lot of options for solving it. I could either try factoring it. If I move the 9 over, I can use completing the square. I can use quadratic formula. I'm going to bring the 9 over. So I have p squared plus 8p minus 9 equals 0. So I got to find two numbers that multiply to make a negative 9 and have a difference of 8. Well, that's going to be p plus 9 and p minus 1. That makes that factor. So p plus 9 equals 0, or p minus 1 equals 0. So p is either negative 9 or p is equal to positive 1. You will notice that I can't keep negative 9, because if I stick a negative 9 in either one of these original logarithms, I'm going to have a negative number in the log. So that number is no good. It's outside the domain, and my only solution is p equals 1. And 1 does not make either of those logs negative. So remember, when you're dealing with a log equation, you should always go back and check your answer to make sure it's in the domain of all the log terms in the equation. All right, so let's move on now to problem number 19. The next problem has us solving another log equation. Hopefully you're thinking that I need to go in and combine those logs together, because I do. Remember again that this is a natural log now. It's too zoomed in. I'm not sure how that got so thin there. Let's erase that and start again. And let's see here. All right, so let's try this again. Maybe I'm just zoomed in too far. So let's try this. All right. Once again, natural log, that multiplication comes from the addition there. So it's x times x minus 9 equals natural log of 11x minus 91. All right, so again, the addition of the logs became multiplication inside the logarithm. I can now either equate the insides because I have the same log on both sides, or I can cancel out the natural log with its base, which we all know is base e. So again, I like inverses. That's how I do things. So this is now x times x minus 9 equals 11x minus 91. If I multiply all that out, I've got x squared minus 9x equals 11x minus 91. So that is x squared. And if I subtract those over, I'm going to get minus 20x plus 91 equals 0. And again, at this point in the problem, you could either complete the square or try factoring it, or you can run it through the quadratic formula. I'm going to complete the square because I want to keep the idea alive for the rest of the semester, and more importantly, I'm not sure what numbers multiply to make a 91 and add up and have a difference of 20. I know they're out there because I've already worked this problem before, but I'm going to stay naive and just complete the square. So I have an x squared minus 20x, leave some room, equals negative 91. Remember, when you complete the square, you take half of the middle number, square it, and add it to both sides. So I'm going to add 100 to both sides of the equation. The left now factors as x minus 10 squared. The right side, 100 minus 91, that's just a 9. And that's kind of my indicator there, by the way, that this does factor. All right, so again, I've got x minus 10 squared equals 9. My next step is to take the square root of both sides. So I get x minus 10 equals plus or minus the square root of 9. So x minus 10 equals plus or minus 3. Solving for x, I'm going to get 10 plus or minus 3. So 10 plus 3 is 13. X equals 10 minus 3 is 7. So by the way, it was 7 and 13 that multiplied to make 91 and add up to make 20. So those are the two numbers you could have used in factoring. All right, so next up, let's now move into checking these, because remember, when you have log equations, you get bad solutions sometimes. Well, if you look at the 7 and you plug the 7 into your second logarithm, guess what? 7 minus 9 is negative 2. The natural log of negative 2 is undefined. You can't do it. So 7 is too small. We can't keep it. 13 keeps everything positive, and that is the solution for this log equation. So again, very important to make sure you check your answers by either directly substituting them or at least looking at what they make when you plug them back in. All right, so move on to the next log problem on this page, and that's going to be with subtraction. If you think back to the beginning of the note quiz, subtraction of logarithms turns into division. So I'm going to first rewrite this as log base 3 of 2 divided by h plus 6. And that still equals 2. Now again, I want to cancel out my logarithms. So I'm going to put a big O 3 here and a big O 3 there. Inverses, I get 2 over h plus 6 equals 3 squared, which is 9. To solve this, I now multiply by the LCD, which is h plus 6 on both sides. And I end up with a 2 is equal to a 9h plus 54. If I subtract 54 from both sides, I get 9 times h equals negative 52. Dividing both sides by 9, I get my solution. H is equal to negative 52 divided by 9. And if I do check this solution and plug it back into that h right there, you'll notice that the number in the logarithm is still positive, because negative 52 over 9 is negative 5 point something, which keeps that whole number still positive. All right, so that right there is the last of our log equations. Now let's move into more applications. All right, so our applications are going to be ranging from some more compound interest to looking at some population growth and some radioactive decay. So let's first take a look at this investment problem with compound interest. We want to take $50,000 and invest it so that after 30 years, the value has grown to $182,000. So what we want to do is take the same formula from before and just plug in what we have and solve for our unknown. And this time around, the unknown is the interest rate, R. So when I substitute everything in, I'm going to have this number, which is 182,496.72, is equal to my original $50,000, my principal, times e to the r times 30, because it's 30 years. All right, so what I'm going to do is now divide both sides by 50,000. And what we're going to do to be on the safe side is we're not going to divide this out to a decimal. Instead, we're going to keep this as e to the 30 times r is equal to the fraction 182,496.72 divided by 50,000. All right, so the next thing for us to do is get rid of the exponential function by using the inverse. So I'm going to have the natural log of both sides. Natural log of e to the 30r is equal to the natural log of that 182, 496.72 over 50,000. And again, the log and the exponential are inverses because they're the same base. So I get 30r is equal to that natural log of that terrible massive number. All right, and then the last step, divide both sides by 30 to get the r alone. All right, so my r is exactly 1 over 30 times the natural log of 182,496.72 divided by 50,000. When you put that into your calculator, you will get approximately 0.04316. And if we round that to the tenths place while converting it into a percentage, we get r is approximately 4.3%. And so that's the number we get. And this is where you could kind of get into a philosophical debate where if I chop it at 4.3, I may not get there. So I'm going to err on the side of caution, especially since this is going on YouTube, and say, you know what, I'm going to call that 4.4%. So I can make sure that I get that much money. Because again, rounding down would probably cost me a few dollars in the process. So rounding up will be safer. All right, next question. We want to find out how long it will take for us to reach $250,000 with that now calculated interest rate. So if I do that, and again, I'm going to go back to the 4.3 because I now want to be cautious on the side of, I'd rather use a lower rate than use the higher rate because I may lose some time in the process. So I'm going to go back to the 4.3. So just from before, remember that r is approximately 4.3%. And again, I want to have my money grow to a total of 250,000 because 250,000 is $250,000. So if I now set up my algebraic equation, I want to reach $250,000. I am starting off with the initial investment. That was $50,000. And that is now e to the 0.043t. Next thing to do is solve the equation by dividing by 50,000. And when I do that, I get e to the 0.043t is equal to 5. To now solve this, I'm going to take the natural log of both sides. So natural log on the left and natural log on the right. Once again, those are inverses. So it takes me to 0.043t is the natural log of 5. Dividing both sides by the 0.043. And I get t is approximately 37.4 years. So 37.4 years is the amount of time it'll take at 4.3%. And again, if I took the interest rate up to a 4.4%, it would probably be less time. It would probably be closer to probably 36 and some change, or maybe 35 and some change, because again, rounding plays a big role when you have exponential functions. Rounding will throw the answers into seriously different directions. And by the way, that was a 30. All right, so let's move on to the next problem, and this is a population growth problem. In this problem here, we're going to have the comparison of an Asian country at two different periods in time. In the start of time, it's going to be 22.9 million people living there, and then a census is taken 10 years later, and the population's grown to 23.7 million people. So the idea here is to look at the growth of the population and find the constant k in the model. So what we want to do first is we want to look at what happens in a total of 10 years. So the population in 10 years is P of 10, and that is P0, which is the initial population. I'll just leave it as P0 for now, is e to the k times 10. The population in 10 years, they tell us, is 23.7 million people. The initial population at the start was 22.9 people, and that's e to the 10k. Just like before, we want to isolate the exponential by dividing by the coefficient. And then we're going to keep that as a fraction. So this is e to the 10k is equal to 23.7 over 22.9. I'm now going to take the natural log of both sides. And again, inverses cancel. I know it's very repetitive. So 10k is equal to the natural log of the fraction 23.7 over 22.9. Then, of course, to get k, we just divide both sides by 10. So k is exactly 1/10 of the natural log of 23.7 over 22.9. And when we round this to 5 decimal places, we'll have 0.00343. And again, rounding makes a big difference in these problems. When I write down my exponential function for the population, it is 22.9 e to the 0.00343 t. And again, what this population model does, it says you give me the time in years, I will give you an estimate of the population of people. All right, so now let's move on to the next page, which has us using this model. For the next problem, we're going to use the model to make a prediction for 20 years at the initial census. So that's going to have us calculating P of 20. So from before, that was 22.9 times e to the k number, which was 0.00343 times t, which is 20. And when I put that into my calculator, make sure you put parentheses around the exponential's multiplication. This is 22.9 times e to the 0.00343 times 20. Very important to have parentheses around that multiplication in the exponent. And when you calculate that, you're going to get 24.526. And again, that's not 24 people, that is 24.5 million people. So this is 24.526 million. Everything was in millions for this problem. All right, now let's move on to number 23. In problem 23, we have radioactive decay, which is kind of the same thing as carbon dating, because the carbon is changing from one form to another. So in this problem here, they tell us that we want to have 75% of what we started with remaining. And we're looking at a mummified bull. So the idea is to use 75% to figure out how much time has passed in the decaying process. So if you have 75% of the original, that means you have 75% of Q0, because Q0 represents the original amount. So that's actually 0.75 Q0 equals Q0 times e to the negative 0.000121t. All right, so again, on the left side is 75% of the start, and on the right side is the model, which gives you the amount. Well, first thing we're going to do here, I'm going to divide that Q0 out of there because it is unknown, and more importantly, it doesn't play a role in our calculation because it cancels on both sides. So instead, we get e to the negative 0.000121t equals 0.75. And you're probably imagining what we do next. Yep, we're going to take the natural log of both sides again. So we're going to take the natural log of the left and the natural log of the right. Again, inverses. We get negative 0.000121t equals the natural log of 0.75. To get the t all by itself, we once again divide. And when you do that, you'll get t is approximately 2,377.5. And this time around, that's years. So 2,377 and a half years is the estimated age of that mummified bull in this problem. All right, so next up, we're going to move into the regression. And again, I'm not going to focus on this for any of the exams or anything, but it is good to talk about how to do it in Desmos. So if you're in Desmos, what you want to do is you want to make sure you use the table feature in the upper right corner. So again, you click in the upper left corner. So in the upper left corner, you click on a table and you enter the values. And then when you're in Desmos, what you're going to do is type in the following. It's going to be y1, so the letter y followed by a 1. Then you're going to hit the little squiggle symbol, which is the shift just to the left of 1. And then it's going to be a times b to the power x1. And what that's going to do is feed those numbers from the table into the calculator, and it's going to give you a model of best fit. So in this problem, when you do that, it will generate the value of A, which is approximately 71.6, and B, which is approximately 1.810. So your exponential model is going to be equal to 71.6 times 1.810 to the t power. So again, that's the exponential function generated by it. If you want to change the form and have it with a base of e instead of the base of 1.8, you can just take and rewrite it as taking the 1.810 and take the natural log of it. If you do that, that is going to give you the base, which will be on the e. And the natural log of that is going to be 0.593 to 3 decimal places. So this exponential model is going to be still 71.6 for the coefficient, but now it's e raised to the 0.593t. All right, so again, one has the base of 1.8, the other one has a base with the number e. In either case, they give you the same thing. The next thing I want to do is make a prediction. So I'm going to use the first model because I like it more. Again, the model from the first problem is 71.6 times 1.810 to the t. So they want us to make a prediction for 8 months. So that's going to be y is approximately 71.6 times 1.810 raised to the 8th power. And that'll give you approximately 8,000 cases of Ebola for this problem. The next thing we can do is look at whether or not this model makes sense indefinitely. And if you think about it, it doesn't make sense because this is an exponential model, and the exponential model of cases will eventually overtake the number of people living in the village. So we can't have that. It's impossible. So the answer to this question, is this reasonable? Sadly, it's not. The answer is no, because the number of cases will exceed the population. And if you go on to take more math after this, you will learn that there's better models to fit diseases. And one of them is called the logistic model, which is given right here. So if you type this in to Desmos, again, using the same table of numbers, it's just going to be y1. And that's going to be, again, approximated by c divided by, parentheses, 1 plus a times e raised to the negative b times x1. Again, using your table numbers, that's how you type it into Desmos. You're going to get c to be approximately 11,420. A is going to be approximately 203. And the B number will be approximately 0.67. So my model is going to be y is equal to 11,420 over 1 plus 203 times e to the negative 0.67t. It's not the prettiest equation, but it's much more accurate. And so now if I make a prediction for 8 months using this model, that is y is equal to 11,420 divided by 1 plus 203 e to the negative 0.67 times 8. When you put that into your calculator, that's going to be 11,420 divided by parentheses 1 plus 203 times e to the power, start a parenthesis, negative 0.67 times 8. Close up the exponent on the e, and then close up your division. And when you type that in, you will get 5,843.57 cases, which rounds to 6,000 cases. And what's really helpful with this model is it tapers off. If you graph this in Desmos, you will see that the number of cases will taper off over time, which makes sense because diseases cannot exceed the population. Finally, we're down to the change of base formula. You've noticed that we've done calculations with natural log many times. You also have a log base 10 or a common log button, but we don't have a log base 3 on most calculators. So what you do is you use what's called the change of base formula. And the change of base formula has you taking the log of any base you want, I will use natural log, of the number you're taking the log of, which is 12, divided by the natural log of the base, which is 3. So that's converting it over, and then if you type this into a calculator, you'll get 2.2619. And what that really means is if you take a 3 and raise it to the power 2.2619, you'll get very close to 12. You're not going to get exactly 12 because we're rounding in this process. For this last one, it's the same idea. It's the natural log of the number we're trying to calculate the logarithm for, divided by the natural log of the base, which is 4. In this case, when you type it in, you're going to get a negative 0.2925. And again, the idea here is if you took a 4 and raised it to this negative decimal exponent, you'll get pretty close to 2/3, but you won't get exactly 2/3 because it is an approximation that's been rounded. All right, so that right there is the end of note quiz number 12, and the idea is to work with exponential and log functions to solve equations and to do some applications. So practice these problems, and you'll be seeing them coming up on the final exam in the coming weeks.